In this tutorial we are going to discuss big O notation, which is first of the asymptotic notations. So let us consider we have a problem for which we have found an algorithm with running time of fn. Now let us draw this function in a graph, and x-axis of the graph shows input size of the problem and y-axis of the graph shows running time of the algorithm. We can draw this fn maybe like this, which is called fn, and this fn shows that the running time of an algorithm is increasing with the input size like this. So now our task is to find another function gn which could be drawn like this, and this function is c into gn, and c is a constant which is greater than equal to 0. If this c gn is greater than function n, function fn, for a constant value c greater than 0 and a value of n which is n naught greater than or equal to 1, then we can say that fn equal to big O of gn. If you want to define it formally, we can say that O of gn equal to fn such that there exist positive constants c and n naught such that fn is greater than equal to 0 and less than equal to c into gn for all the values of n which are greater than or equal to n naught. Then we can say that fn is equal to big O of gn. Now what we can do, we can understand this definition using an example. So let us consider an example where fn equal to 3n plus 4 and gn equal to n. So for these function, can we say that fn equal to big O of gn? Now let us put these values in the equation. Fn should be less than c into gn. So fn is 3n plus 4, it should be less than c into gn, which is n. If we look carefully at this equation, we can put a value c equal to 7, 3n plus 4 should be less than 7n, and now we can find out a value for value of n for which this condition is satisfied. So this should be 4n should be greater than 4, which is n greater than or equal to 1. That means we have found a value of n which is n naught. If it is greater than or equal to 1, then we can say that this condition is being satisfied, and hence we can say fn equal to big O of gn. If we replace this gn with any other function like n square or n cube or 2 to the power n, and all these functions are greater than or equal to n, then for all these functions we can say that fn equal to big O of Gn, because all these functions are greater than n, and we have find out upper bound on the function fn, which is n. That means all the function which will be greater than n, for all those we can write this notation. Technically speaking, we are correct in saying that fn equal to big O of Gn for any of these functions, but our aim here is to find smallest rate of growth, that is Gn, which is greater than given algorithmic rate of growth, which is fn. So that means our aim is to find tight upper bound, and when we find out tight upper bound on a function, we also say that this is worst case running time of an algorithm. In our next tutorial, we will be discussing about big omega notation. Thank you so much.